everybody. Today, we're going to talk about sequences. It's another rather short chapter. So we're going to do sections 1, 2, and 3 today. Do the quiz next class. Finish section 4 of the class after that, and then be taking the test the following. So again, we're going to try to cram this all down your throats before you guys leave for winter break. Yeah, well. So we're going to just start with a little bit of vocabulary. So when we talk about a sequence is just a type of function. So remember, a function takes some inputs, some x's, and sends it to some output, some f of x. So when we do function notation, our independent variables like our x, so we write like f of x equals, and then some dependent expression, some expression depending on x, like 2x plus 5. So a sequence is very similar. It's another type of function, but here the domain is particular. We talk about a function in general, the domain could be almost anything. When we're talking about a sequence, the domain is specifically the natural numbers. What are the natural numbers again?
Like whole numbers above 1?
Yeah, you're counting numbers, right? Sometimes the natural numbers start with 0. Sometimes they start with 1, depends on the context. I think for the IB, they start with 1. I always do start with 0. So the way you'd write a sequence, instead of writing like f of x, you write f and then a subscript with your independent variable name. Typically, we use the letter n in a sequence. And then we equal some expression that depends on that independent variable, like 2n plus 5. So this independent variable, this n, we refer to as like the term number, and the dependent, the output, would be like the term value. So if we read f of 5 is equal to 18, the way we'd interpret that is the fifth term in the sequence is 18. Is everybody okay with like the notation and the vocabulary we're using here? Again, I want to be real clear on this because it makes communication way easier if we feel we're all on the same page in terms of what we're writing and how we're writing it. So if we want to talk about sequences, one way we can classify a sequence is by how many terms it has. So for example, the sequence F has the terms 1, 4, 9, 16, and 25. Notice that doesn't go on forever. We call that a finite sequence. As opposed to sequence G that contains the terms 1, 4, 9, 16, 25, ... That ellipsis implies that this pattern continues forever. This would be an example of a infinite sequence. Does everybody feel good about the difference between, say, finite and infinite? Okay. So if we have the sequence B sub n, and we want to list the first 5 terms, well, the first term would be B sub 1. And to find that value of that term, I'm just going to plug 1 in for n and then evaluate. If I look at B sub 2, and then B sub 3, and I just kind of continue plugging in. There's no trick here. Everybody feel okay about how to use a sequence to find some terms? Basically just the same way as a function, right? just change the notation a little bit, but no big deal. We can also use a sequence to model a situation, like with a story problem. So this example says a 180 liter bathtub contains 50 liters of water and is being filled at a rate of 10 liters per minute. How much water is in the tub after 5 minutes? So I might think about this as a sequence where n is going to be like the number of minutes. So initially we contain 50 liters, and then every minute 10 more come in. So I direct my sequence that way. So how much water is in the tub after 5 minutes? Well, that's just f of 5 then. So I'd have like 100 liters. When will the water overflow the tub? How much water can the tub contain? 180. So that's like my term value. So I have this, right? And then I can solve for n. I'm not going to show the algebra there. So how would I answer this question now? So after 13 minutes, right? At 13 minutes, is the tub overflowed? No, it's just like right at the brim though, right? The next instant after 13 minutes, so again, that word after there is doing a lot of work for us. How else could you write that? You could say n greater than 13. The drain is open when the tub contains 50 liters of water and is also drains out at a rate of 15 liters per minute. How long to empty the tub? Well, I had the 50 liters. You have 10 liters per minute coming in, and then 15 liters per minute going out. So my new sequence would be that guy, right? When is the tub empty? How do I know the tub is empty? Yeah, when there's 0 liters of water, so we put 0 in for f of n. And then we just solve for n, get 10 minutes. Everybody feel okay? Fairly simple, right? This is like a pre-algebra level story problem. Situation is pretty clear. There are 2 special types of sequences that we're going to work on in particular. Those are arithmetic and geometric sequences. So when you hear arithmetic sequence, you need to think linear function. Basically, everything that you could do to deal with a linear function, you can use to deal with an arithmetic sequence. We have 2 kind of canonical ways to represent a sequence. We can use an explicit formula or a recursive formula. An explicit formula is always going to be in terms of n, the term number. So that means with an explicit formula, if I want the 50th term, I just plug 50 into n and compute, right? The other option is a recursive formula, which is built on the previous term. So if I want the 50th term, I need to know the 49 terms before it, really. Everybody's okay there? Heck, Mr. Goulet, that seems pretty obnoxious. Why in the world would why would anybody want a recursive formula? Well, 2 reasons. One, typically it's easier to write the recursive formula. And 2, although repeated computation is kind of a hassle for us, you know, who digs that kind of work? Computers. So it's very easy to write the equation, have a machine or a calculator or computer compute repeated arithmetic. It's very, very good at that. Everybody feel okay? Let's look at some examples. Oh, do we know what the letters mean in this? I didn't mention this. What is a sub 1? The first term, right? What's the D? That's called the common difference. It's basically slope. Because if I look at this arithmetic, or this explicit formula for an arithmetic sequence, you know what this reminds me of? Is a point slope equation for a line where my point is 1 comma a sub 1 and my slope is d, right? You see that is really the same thing. So we'll use that at some point. All right, let's say that we have this sequence of terms and we're asked to write the explicit recursive formulas for this sequence. So the first thing I want to do is try to identify the type of sequence. So we'll talk about arithmetic now, we'll talk about geometric in a few minutes, and then there's any other type of sequence is not one of those two, right? So the defining characteristic of an arithmetic sequence is a common difference. That means that if I subtract 2 consecutive terms, I should get the same number every single time. So going from 2 to 11, what did we do? Add 9. And from 11 to 20, and from 20 to 29, 29 to 38, and 38 to 47. Same common difference between them, right? Is everybody okay with that? Now, Mr. Kulik, do I have to check between all the terms? Oh, yes, you should, because Mr. Kulik is mean enough that he might give you a sequence where like the first 3 or 4 terms have the same common difference, but like the last one doesn't. That feels like a trick I would play on you. Don't be fooled. I'm warning you now. So that's us confirming this is an arithmetic sequence, but we also accomplished something else. What else did we find when we did this? We also found D. That number that we've repeatedly added or subtracted to get to the next term, that is our common difference. Everybody okay? So if I want to do an explicit formula, so here's my formula. I'm going to fill in. What's my first term? 2. What's my common difference? 9. What am I going to do now? Just kind of distribute things through and simplify and boom, bingo, bango, bongo. There's my explicit formula. Everybody feel good there? That's what the formula is. You do it for the second term, and you put a 2 instead of a 1, you get the same result. let's write the recursive. So that's my formula for the recursive sequence, right? What does a sub n minus 1 mean? Just means the previous term, right? So that never gets anything filled in when it's a formula. You know, D is 9. But I need to include one other thing with the recursive formula. I need to have a starting point to start building the sequence, right? Because to get the next term, I need a previous term, so I need some place to start, right? What term should I use as my start? The first term, which is 2. So I also need to list that when I write a recursive. A starting place. So now if I wanted to find a sub 2, that would be a sub 1 plus 9, which is my 11. And after I have a sub 2, I can find a sub 3. And after I have a sub 3, I could find a sub 4, and then go on and on and on, as long as you want it. I'm bored already, though. Feel okay on plugging this stuff into a formula? To make this a little bit more challenging, instead of giving you like consecutive terms of a sequence, we can give you like some arbitrary terms. Now here we're given some important information at the start that we're told that we have an arithmetic sequence. If I don't have that, there's nothing really I can do with just two terms. I have to know the type of sequence you want me to write, because the 2 terms on its own are like, oh, I don't know, whatever, man. I can do anything I want with these 2 points. Okay. How do I do something like this? I'll tell you the easiest way to deal with this. Is I'm going to think about each one of these as a point. Everybody's okay with that? And remember, an arithmetic sequence is just like a linear function. So all I'm trying to do is write the equation for a line that passes through these 2 points and just communicate that in the language of a sequence. So the first thing I'd want to do if I was writing an equation for a line is calculate the slope. Since this is an arithmetic sequence, that's called the common difference. But I calculate it the exact same way. Everybody's okay with that? Now if I have a slope, I can use the point slope equation for a line. Now in the language of sequences, y is a sub n and x is n. The m is the slope, the common difference. And then y1 could be either 5 or 11. And the x1 will be corresponding to whichever y you pick. I'm going to pick this one because the numbers are smaller. And then I just clean up. What do you guys think? Isn't it nice when it's just like, hey, we're just doing this? It's like the exact same thing still, yeah? Yeah. For arithmetic, exact same thing. So. Oos. Everybody feel okay with that? Now you could use the arithmetic sequence formula and like manipulate that, but like Why invent a new method? This thing that we just did works here. Let's just do the thing we just did, and we'll just rewrite the variables as sequence variables at the end. And like, I don't want to make it harder than it needs to be. Right? We just got good at this. Let's keep doing it. All right. Again, we can apply these to real-world situations and use them to solve like story problems. So here we're told Susie decides to deposit an initial amount of $1,200 into a savings account on June 1st. The account pays 5% simple interest on the initial amount. Assuming no deposits or withdrawals, how much money does she have after 10 years? So this term, simple interest, is important. Who remembers the difference between simple interest and compound interest? Because those are probably the two terms you've heard, right? Here's the difference. Simple interest is only earned on whatever the initial deposit was. Compound interest is earned on whatever money is in the bank account at that time. So the simple interest is always the same every single year. Compound interest is going to be a bigger amount because you have the initial deposit plus the interest from the previous years in the account. So it'll compound. Everybody okay? So the first thing I'm going to do is calculate my simple interest. So 5% onto 1,200 is 60. That's the amount that we're adding to this bank account every year. That means that this is 90. Is okay there? Okay. So if I think about this as just like y equals mx plus b, I know my m is 60, y is a sub n, x is n, and then what is the y-intercept going to be? How much money is in this bank account at year 0? 1,200, right? Oh, look at that. There's my sequence. Everybody feel good there? After 10 years, well, that's easy. $1,800. Not great, Susie. 600 bucks for doing nothing is great, but over 10 years, not great, Bob. You feel okay there? So here, we're given 3 consecutive terms, the 50th term, which is 6, the 51st term, which is 11, the 52nd term, which is 16, and we're asked to find the first term. I don't know why they gave us 3 terms here. You can do this with 2. What am I going to do? Yeah, I'm just going to do the same thing we did before. Convert them into points. Write my explicit formula for a sequence, which would be the same as writing my equation for a line. And then once I have that equation, what am I going to plug into it? 1. And then I'm done, right? Everybody okay there? Notice that I didn't need 52 comma 16 at all, other than to confirm that this would be arithmetic. Right, we've added 5 each term. Where'd I get the what? That's a 51. It's just a bad looking 5. Bad damage. Thank you. Everybody feel okay? Your other special type of sequence that we'll worry about are geometric sequences. So the formula for a explicit formula for a geometric sequence is the first term times r to the n minus 1, where r is the common ratio. It's essentially what you're multiplying by each time. And the recursive is the previous term times the r. So let's say we have this sequence here. First thing I want to do, if I'm asked to write its explicit or recursive formula, is to identify the type of sequence. So typically I would check to see if it's arithmetic first. So here I would say, okay, well, I minus 15, and then, oh, I would have added 60, stopping. Is it arithmetic? Nope. Okay. So let's see, maybe it's multiplication. I'll write an X, that's confusing. So times by negative 4. Oh, good. And then I times by negative 4, and then times by negative 4, and times by negative 4. This is geometric. Okay? So that tells me that the r is negative 4 and it's geometric. So my explicit formula is the first term times r to the n minus 1. And my recursive formula would be r times the previous term. And then I also have to list a starting point. Let's make that use the first term. Everybody feel pretty good there? Should be very easy, right? We're just kind of plugging stuff into the formula. The r is easy to find. Keep in mind that that r could be a fraction, right? It could be like 1/2, where you're multiplying by 1/2 each time or something. That's okay. Not if it's geometric. If the r's are different, it's not geometric. Is that okay? So if you get a differing number, it's not geometric. If it wasn't arithmetic also, your answer to what type of sequence this is neither. Good? Okay. Let's say we're given 2 arbitrary terms and asked to write the geometric sequence. Again, you have to be told in this sort of problem what type of sequence you're writing, because just the 2 terms, you can't tell if it's arithmetic or geometric. There's no way to know. They have to tell you. Unfortunately, this one, arithmetic sequences, those were linear functions. Geometric sequence is like an exponential function. So there's not a good way to recover the r from this information. So what I'm going to do is I'm going to think about these, again, as kind of like points where I have an n and a sub n. And I'm going to take my recursive formula. And I'm going to plug this n and a sub n in. And I'm going to also take that n and a sub n and plug them in. That's going to form a system of 2 equations. I'm going to do a little bit of cleanup there and just subtracting the exponents. And then I'm going to solve this system. I'm going to refer to the first equation as equation A and the second equation as equation B. To solve this system, my choice is going to be to use elimination. Now the catch here is what operation is going on between the variables? Between the A1 and the R. What symbol is there? Multiplication, right? When we've done elimination before in Algebra 2 or pre-calculus, the variables were always being added or subtracted, right? So when you did elimination, you added the two equations together to cancel the variables. Here, though, because the variables are being multiplied, we're going to divide the equations in order to cancel the variables. So I'm going to take the equation with the bigger exponent, that's equation B, and divide it by the equation with the smaller exponent, that's equation A. Now it doesn't really matter the order you do it, it just algebraically it's a little bit neater if you do it that way. So I'm going to have on the left hand side, I'm going to have equation B divided by equation A. And then on the right hand side, I'm going to have equation B divided by equation A. Everybody okay with what I did there? 3 divided by 243 is 1 over 81. A1 cancels out for the top and bottom. And what's r to the 6th divided by r to the 2nd? R to the 4th. Everybody feel good so far? Okay. How do I solve for r here? How do I cancel out that exponent of 4? Yeah, it's called a fourth root. Yep. So you put the little 4 in that check mark. That's the index called the index. Now, because that index was an even number, what do we have to remember? Plus or minus. So we have actually plus or minus. So the fourth root of 81 is 1/3. And we're going to end up with two sets of answers here. One where the answer has a positive r and the other where the answer has a negative r. That's fine. So far, so good. Now that I've solved for r, let's go back and find A1. How do I do that? I'm going to go back and plug it into either equation A or equation B. Does it matter which one I choose? No. So let's just use equation A. Now notice that because the exponent here is even, it doesn't matter if I plug in the positive 1/3 or the negative 1/3. The squared is going to give me a positive 1/9 angle, right? So I'm going to get the same A1 regardless of which value for r I choose. Great. And then when I multiply both sides by 9, really, it's too early for that stuff. 9 times 243. My powers of 3, I don't know past 243. That's where I kind of draw the line. 2187. Does everybody feel okay here? Okay. So my final answer would be 2187 times positive 1/3 to the n minus 1, or 2187 times negative 1/3 to the n minus 1. We have two answers there. You guys feel good there? And if I wanted to write this as a recursive, you know, I could do that too, right? Once I have the first term in the R, it's pretty easy. What do you guys think?
Good.
Yeah, right? No big deal. Okay. A common application for a geometric sequence is compound interest. So I'm presenting to you the compound interest formula here. So A equals P times 1 plus R over N to the NT, where A is the account value at some time T. Really, maybe we should write this as like a function like A of T. That's maybe a little clearer, right? Where it's just some function at, or a value at some time. P is the principal, that's the initial investment. R is the interest rate as a decimal. N is the number of compounds per year. And then T is time in years. Okay. So example here, it says Sam puts $15,000 into a bank account. That's my principal. Earning 6% annual interest. There's my R. Compounded monthly. That's my N. How much did the account, or is the account worth in 10 years, or sorry, 20 years? That's my T. So if I want to write my equation, I'd say like A of T equals 15,000 times 1 plus 0.06 over 12 to the 12 times 20. I guess 12t. And if I want the value at 20, we do that. Just type that into our calculator. You guys feel comfortable typing that kind of stuff into your calculator? That would be appropriate to answer with a yes or a no. Okay. Just checking. 49,653 and 7 cents. Mr. Kulik, why don't you round that to 3 significant figures? Because what? Because it's money! Money! What do we round monies to? The penny. Yeah. Oh, okay. Part B then asks how much interest was earned in that time. Well, shouldn't that just be like A of 20 minus A of 0? Right? Any difference between where we're at and what we started with, that has to be from the interest payments, right? So we started with 15,000. So we earned just a shade under $35,000 in interest. Not too shabby, guys. Next question, or example, I should say. We have $1,000 to invest and wanted it to double in 10 years. What interest rate do I need, assuming we're compounding quarterly? Okay, so this is P. This is T. Double is like A of 10 is equal to 2,000. What interest rate? That's what we're searching for. Compounded quarterly tells me that my n is full. Everybody feel good? Okay, let's fill it in. So I have 2,000 equals 1,000 times 1 plus r over 4 to the 4 times 10. And we're solving this for r now. First thing I would do would be what? You said something. I just couldn't hear you. You kind of mumbled it. Okay. What do we do first? Solving for r. Divide by 1,000, right. We have to get rid of this guy before we can worry about the exponent over there. Okay. Now what? Are we going to cancel out that power of 40? Blake, how do we do it?
Do it.
How do I cancel out that power of 40?
You have to square power of 40 on both sides.
Yeah, 40th root, right?
Yeah.
Now, technically, since that's an even root, I should get a plus or minus. Do I really need the plus or minus here if we're talking about like interest rates? Everybody's getting a negative interest rate, right?
Yeah, maybe.
So we won't worry about that. And now that's the 40th root of 2 is just some terrible looking decimal. I'm not going to worry about making the decimal right now. I'm just going to wait and do it all in one stroke on my computer, try my calculator. Last steps would be to, how about we subtract the 1 first and then multiply by the 4? Usually that's what we do when we're solving, right? We undo the multiplication division before we do the multiplication division.
So 4 times -1 plus the 40th root of 2.
How do I do the 40th root on my calculator, Mr. Kulik? So you could do that. Yeah, you could use the math button and type in the index. You could also type it in as just like 2 to the 1 over 40th. That's okay also. That's the way I did it when I typed it in. So we would want like a 6.99% interest rate. How do you guys feel on that kind of thing? Okay. Before I finish up, I just want to show you a little thing that we can do on our calculator that may interest you. Yeah. All right. So what I want to do is I want to go back to this type of problem where we wrote this arithmetic sequence from 2 terms, right? Now, we did that by hand, not a big deal. Calculator can do this for us also. If I'm taking an AP or IB exam, I have the calculator the entire time. There's no restriction on it. Am I ever going to do this problem by hand? I would have the calculator do it because the calculator's not going to make, like, drop a negative sign or write down a number wrong or anything else. It's going to do it for me perfectly. All I have to do is enter it in and ask it. So the way to do this is I'm going to enter these 2 points into my calculator. So I'm going to press Stat. I'm going to, from the Edit tab, I'm going to pick the Edit command. And I'm going to type in the 0.15 and then the 0.511. Everybody good? 0.5, 511. I'm going to exit out of here. And I'm going to do stat, calc, linreg, because a arithmetic sequence is just a linear function. I don't care about storing it anywhere, so I just want the L1 and L2. 1.5n plus 3.5. Exactly what the calculator spit out. Very nice. Well, that's fine. What's even better, though, is I can do this for a geometric also. The only difference is a geometric sequence is the same as what kind of function? Exponential. So the only difference I'm going to do is instead of doing linreg, I'm going to do expreg for exponential. Oops. Okay, so 243, 73 is my points. Stat, calc. Now expreg is down here towards the bottom. There it is, number 0. Wait a minute, Mr. Kulik. That's not the A that you gave us. What's the deal? Is the calculator wrong? Were we wrong? What happened? So we're both right. Notice the form that the calculator is giving us. We would write this as A sub n equals 6, 5, 6, 1, 1/3 to the n. Notice here, this is to the n minus 1. That's the difference. That's why the first number is different. But if I plug in 1 to this, I'm going to get 2187. Right? So it's the same equation. Promise. If I plug 1 into this, I get 2187. If I plug 2 into this, and 2 into this one, then I get the same thing. Promise. They're giving me the same answer, just writing it in a different form. Okay? What do you notice, though, that the calculator didn't catch here? The possibility that the 1/3 could be negative also. So that the calculator didn't catch. And it can't. Because by definition, exponential functions can't have negative bases. So it's not going to catch that for you. That's kind of it for me for today. I think that covered everything we wanted to do. Yeah. Next time, we're going to do the Chapter 3 quiz. So you should be able to, given a sequence of consecutive terms, determine if it's arithmetic, geometric, or neither. That should be pretty easy, right? Use an arithmetic sequence to do currency exchange problem, story problem. And then from given information, find the nth term of a sequence and compute the value of the specified term. So whether that's, I've given you like a sequence of terms, or I've given you a couple of arbitrary term values, you know, like we're just writing explicit or recursive formulas, and then using that to compute, compute a value. What do you guys think? Pretty simple, right? It's a quickie. The homework that I'm going to assign for Chapter 3, I'm just going to have you do the review because we're going to knock the entire chapter out in 2 days. And like some of these sections have a lot of homework questions. The review is a long one also. So my suggestion is, unfortunately, the review is mixed. Like problem 1 includes things from like sections, all of sections 1 through 4. So I don't know that starting the review right now is a great idea. I would just pull some arbitrary homework problems from sections 1, 2, and 3 to do as practice for the quiz if you're looking to study. I probably wouldn't bother starting the review because there's going to be stuff that you just can't do yet, unless you remember everything about series from last year. But you could sit on that. Does that feel okay?
So, quiz next class.
Quiz next class. And then we'll finish the rest of chapter 3, and then we'll do the chapter 3 test the following class. We're into the fast and furious part of the year where, like, these are all topics we've done before, so I'm just kind of doing a little light review, and then just like, you guys need to do some practice and take a test, and we're moving on to the next thing. There's a lot of these like straight topics that we've spent some time with in our pre-calculus or Algebra 2 classes that we're just going to kind of motor through. Cool? All right. I'm done here for you guys.
There's the bathroom.
Sure.